if you're interested in transferring to CU Boulder next Friday, the 8th of November, there's pretty much an all-day event at that campus. There will be carpooling, so if you don't want to drive that way, people are meeting here on campus and carpooling to CU Boulder. The agenda and the flyer are posted here. So if you just want to like look through that to see if you're, if you'd be interested in doing any of these things, various types of engineering. If you're interested, I have this sign-up sheet. You can sign up now, or if you want to think about it, let me know and I'll forward your name along to the person in our department who's coordinating all of this. So just send me an email if you want, but information is there at those two documents if you're curious. And also, since we missed a day, I think in order to catch back up, I'm going to forego any homework questions for the moment. If you have questions, feel free to email me. I can respond to you that way. But we really have to pick up the pace since we're falling even further behind. So with that said, we'll start with, we'll finish 10.5 today, and then we'll start 10.6, maybe finish that, maybe not. And if we have time, we'll start 10.7. Excuse me. All right, in 10.5, we were looking at comparison tests, the direct comparison test, and then we moved on to the limit comparison test. And just a quick reminder of what the limit comparison test was. So just like with the direct comparison, we were going to choose some series to compare to. But unlike the direct comparison, we don't have to establish a relationship between A and B, because all we're going to do is take A and divide it by B, compute the limit out of infinity. Depending on what that limit turns out to be, one of these three scenarios, and what the series that we chose to compare to actually does, whether it converges or diverges, and what that limit is tells us the nature of the series A sub k that we were given. So we started off with this example. And we said generally we're going to choose a series that's comparable to the given series. So we said, well, this is like 3k over 3k to the 3/2, which is like 1 over the square root of k. And we said that was a divergent p series because the power is less than 1. So the series that we've chosen to compare to is a divergent series. So once you pick a series that you're comparing to, you got to know the nature of it. Does it converge or diverge? Sometimes it could be the case that the series you pick, you might have to do a separate test to determine whether it converges or diverges. But then once we know that, for the limit comparison, I think it's preferable over the direct comparison in a lot of cases because you don't have to establish a relationship, which one's larger, which one's smaller. We just immediately go into computing the limit at infinity. So the limit as k approaches infinity, we're going to take our given series and divide that by the series that we chose. So instead of dividing through by 1 over k to the 1/2, I'm just going to multiply by its reciprocal. So there's the limit at infinity on a over b. And so we just compute that limit. Since we're going out to infinity, we have a polynomial in k over a polynomial in k, essentially. Not quite, but the leading term up top is just that 3k times that k to the 1/2. So we're going to just look at that. 3k times k to the 1/2 gives us that. and the leading term on the bottom is 3k to the 3s. So that just simplifies to 1. The limit at infinity is 1 as well. Close that other door too. So we've got a limit comparison. The limit is equal to 1. What is that? What is our conclusion?
Divergence.
Yeah. Really, the conclusion of the limit comparison test says that if you get a finite number that's not 0, that both of those series do the same thing. So since L is equal to 1, means both series do the same thing. Since the series we chose diverges, the given series also diverges.
So if it equaled 1 and the given series converged, it would converge?
Right, yeah. If we got a limit to be 1 and the series we chose converges, then both series would converge. So we'll just write this out explicitly. The given series converges. Or diverges, sorry. And hopefully as you go through these tests, you don't really find, I don't think the tests themselves are necessarily that complicated. I think the issue here is remembering all of the conditions on all of the tests. Like if I perform this test and I get a particular result, what does that mean? Versus the next test, what does this result mean? All right, so any questions on that? Limit comparison test for that series. I think the other advantage of the limit comparison is that really the series that you choose rather, it doesn't really have to be super related to the series that you're given, right? Just the limit comparison just says as long as you know something about the series that you choose, whether it converges or diverges, you can determine in a lot of instances, you can determine whether the given series converges or diverges. So, in fact, we could have chosen any series here. With the direct comparison, it's typically you want to choose a series that's closely resembling the given series. That way you can make a comparison to the given versus the chosen pretty easily. But with the limit comparison, it doesn't matter. You just pick any series you want. Okay. We'll look at an example. When we get to example 5, we'll look at a couple of situations with that, but that's how that works. Does anyone have any questions on that? And again, the nature of this, I believe we discussed kind of in passing, but the nature of this is we've got the limit at infinity of a quotient. And if that comes out to be a finite number, what that means is that A and B are both growing at a comparable rate. And when A and B grow at a comparable rate and A converges, so does B. If they're growing at a comparable rate for condition 1 here, and one of them diverges, then the other one has to diverge as well. If the limit of their quotient is 0, what that means is that the series B is growing much more rapidly. And so if we've got a convergent series that's growing more rapidly or converging more rapidly than A, then A has to converge. If the limit's at infinity, then A sub k grows more quickly than B. And if B is diverging and A is growing faster than a divergent series, it has to diverge as well. So that's kind of the growth rates kind of justify why the limit comparison tests work. Okay, so how about 1 over 2 to the k minus 5? Again, don't just say it converges or diverges. Be able to justify why it converges. So, I guess starting out with the divergence test is probably where you should start. If you have no bearing on what test to use, then just start out with the divergence test and compute the limit at infinity of the given series. So we see that's 0, and what does that mean? What does the divergence test mean if it's 0?
It doesn't. We don't know.
Yeah, it doesn't tell you anything. So the divergence test is inconclusive. It's not a telescoping series. It's kind of related to a geometric series, right? It's not quite geometric because it's not just 1 over 2 to the k. So in an instance like that where I recognize, hey, that series is like similar to here a geometric series, then just compare it with the geometric series. So we'll say we'll do a limit comparison test with the chosen series to be 1 over 2 to the k. What do we know about 1 over 2 to the k? Remember, this is 1 over 2 to the k. So you're thinking of P series.
I think it converges.
It converges, right? Geometric series converges.
Yeah.
Since the ratio R is 1/2, what's the condition for a geometric series to converge? The ratio has to be less than 1 in absolute value, right? Okay, so we're comparing to a convergent geometric series. So then all we do is compute the limit at infinity of the given series divided by the chosen series or multiplied by the reciprocal of the chosen series. So what would our limit be? 1, right? It's 2 to the k over 2 to the k. Okay. Well, let's call this capital L, like they're calling that in our textbook. So again, we've got a finite non-zero limit. Just like in that first example, your limit is finite and non-zero. It means that both of those series do the same thing. So since the chosen series converges, the given series 1 over 2 to the k minus 5 also converges. Okay. So we'll just say this series converges as well. Where do we 1 to infinity? Again, what we're showing is that those two series grow at comparable rates, and we've tested it with a convergent series. So the 1 over 2 to the k minus 5 is growing at a comparable rate to that of a convergent series, so it converges. y'all have any questions on this? Yeah.
So why do you choose 2 times, or times 2k? Why do you apply that?
Here in this step, like right here, just because the limit comparison test has us computing this capital L is the limit at infinity on the terms of A divided by the terms of the chosen series. So we just took the terms of A here, 1 over 2 to the k minus 5, and divided it by 1 over 2 to the k, which was our B. Any other questions? Okay. So then, let me skip up here. Then example 5, he says use the limit comparison test to determine if that series converges. So what would we choose then as our B? And honestly, does it matter what we choose for B? If we're using the limit comparison test, it really doesn't matter. It might in the overall scheme of things, but the initial choice of B, it really doesn't matter. We're not making a direct comparison to those two series. So the series we choose, we really don't care if it's larger or smaller or the same as the series that's given. Yeah?
Did you choose 7k over e to the k over 5?
All right, that seems reasonable. Just leading term over leading term. Yeah, does that seem all right? So then really the only downside of choosing this, although it's like really similar to the series that we're given, I think the downside of choosing this is determining whether 7k over e to the k over 5 converges or diverges. So that's really what we have to know now. Does this converge or diverge? Well, the divergence test is equaling 0, so it's inconclusive again. It's not telescoping, it's not geometric.
Can we just do growth rates and how that function to the k power grows faster than k?
Yeah, so what do growth rates tell us when we apply it directly to the 7k over e to the k over 5? It just says that the nth term or the kth term approaches 0. So when you look at growth rates in that sense, when you say, all right, let me just look at the limit as k approaches infinity, all you're looking at here is the divergence test.
Okay.
Equals 0 by growth rates, but again, that's the divergence test, which is inconclusive. So, divergence test is inconclusive. So what other tests could we use to determine if 7k over e to the k over 5 converges or diverges? Integral test, right? I'll just put it here. So that's a lengthy process, right? Not only do we have to justify this continuous function, we have to determine, is that function continuous? Is that function positive? And is that function decreasing? Otherwise, if one of those conditions isn't met, the integral test would not apply. Oops, that should be an x. So this function clearly is continuous. It's never, we're never dividing through by 0. Is that function always positive? Series goes from 1 to infinity, the function will be considered on 1 to infinity. Well, e to the negative x over 5 is never negative, right? It's always positive, and 7 times a number in between 1 and infinity is always positive. So usually those two conditions are pretty straightforward. It is continuous, it is positive. Is it decreasing?
Yeah,
Yeah, how do we show that it's decreasing?
divergence.
We could say, all right, well, the terms that 7x over e to the x over 5 approaches 0, which means the terms are getting smaller and smaller. So the limit as x approaches infinity, what do we choose? 7x over e to the x over 5 equals 0. That is, the terms get smaller and smaller. So if you're trying to answer it that way, sometimes growth rates are helpful to answer that question. Other times you might have like a L'Hopital's rule involved in doing that. So that could be an option. We could also look at the derivative and test the first derivative. So we verify those conditions are actually true. Then we integrate from 1 to infinity of 7x e to the negative x over 5. So how are we going to integrate that? By parts.
You can go ahead and take the 7 out, right?
Yeah, you can take the 7 out. Remember, if we take that 7 out, we don't even have to deal with the 7 in the integral, because really we don't even have to deal with the 7 in the series, because something that converges that's multiplied by 7 will still converge. Something that diverges and is multiplied by 7 will still diverge. But yeah, if you want to just keep it consistent and leave that 7 in there, there's nothing wrong with that. This is integration by parts. It's similar to many examples we've seen in class. We had a similar example on our exam even. So just for time purposes, I don't want to go through the integration of that. But integration by parts, and we'll find that this integral is finite. That is, it converges. And since the integral converges, what do we know about the series? It also converges. Remember, either the integral converges and so does the series, or the integral diverges and so does the series.
But the integrals in series and tell us that we're converging, right?
Right, what we get as the answer to this integral is not what that series converges to. Right, the value of the integral in general is not the value of the series. Okay, so we're going to go back up here then and say that this converges. By this integral test. Okay, so we've got our series. We chose this particular series, used the integral test on it to determine that the series we've chosen is a convergent series. Now we need to actually compute the limit or do the limit comparison. So the limit is the limit at infinity on the given series divided by the chosen series, or times the chosen series reciprocal, which was, we chose this here. Okay. So what is that limit going to give us?
1.
1. Yeah, you have leading term up top is 7k e to the k over 5. Leading term on the bottom is also 7k e to the k over 5. Okay, so the limit is 1, which again means that both of those series A and B do the same thing, and we've determined that B converges, so A has to converge as well. Here's A sub k and B sub k. Thus, we'll just say thus, the given series converges. So you could, some of these could be pretty involved, depending on the test that's necessary or the test that you decide to use. By and large on the exam, I would have something similar to use the limit comparison test or use the integral test to determine. That way you're not really trying to guess which test you should use. There are certain tests like the geometric and the telescoping that you should be familiar with, whether that was given to you or not. But most of these, I would state which test to use, because otherwise it can be time-consuming even trying to find a test that you can use and or gives you any information. Okay, questions on example 5? Yeah.
For the, like, the limit escape versus infinity and the convex test, is that, those are just other options that you're back to?
Yeah, those are options we have to determine if that function is decreasing, which is a necessary condition for the integral test.
Yeah.
All right, so let me just add a new page here. We'll stick with the same series. In example 5, that one we just did. But this time, let's choose our b sub k to be, let's just say 1 over 2 to the k. So we know that this series converges. And let's see what happens when we compute the limit on these two things. So there's our A. Divided by our B. So what would that limit be? If we chose 1 over 2 to the k?
Maybe 1?
What do y'all think, 1? So as far as limits at infinity, we've got our leading term on top. It's dominated by 2 to the k, and leading term on the bottom is e to the k over 5. So how about that limit? And it's infinity over infinity, right? So if you didn't know what direction to go from here, then you've got to apply L'Hopital's rule to the numerator, derivative of the numerator, derivative of the denominator. But here we can use growth rates as well, right? Even though they're both exponentials, which exponential grows faster? The what? So 2 to the k or e to the k? What's the number e?
Bigger than 2.
It's larger than 2. So which one would grow faster? 2 to the k or e to the power? Right, because it's a bigger base. It's a bigger number being raised to a power. Even though this power is cut down by 1/5 each time, that's the thing with growth rates. Towards the origin or towards smaller indices, it may not be the fact that e to the k over 5 is larger than 2 to the k, but eventually is what that growth rate theorem says. Eventually these functions grow faster than these functions. I don't know if we can capture that, but we'll certainly try. So 2 to the x in red, e to the x over 5 in blue. Probably won't capture it. I mean, it certainly looks like 2 to the x is growing much more rapidly, even as we go out here. Maybe we can't capture it, I don't know. It's not looking good. We're at 10 to the 15th. Still 2 to the x is outweighing e to the x over 5. All right, so maybe we're not convinced. If you're not convinced, then let's do L'Hopital's rule here, because this is infinity over infinity. Let's see if this helps. It might be kind of messy. What's the derivative of 2 to the k? Nope. It's exponential, not a power. So derivative of exponentials, 2 to the k times the natural log of 2. So the problem here is, well, maybe we don't see that yet. What's the derivative of e to the k over 5? One-fifth e to the k over 5. So the problem with L'Hopital's rule is it doesn't get rid of the exponentials for us. Like, they're always there. They're just multiplied by different constants each iteration of L'Hopital's. Still infinity over infinity. Right? Forever. So that's one of the reasons people came up with growth rates, is to answer this very question.
Just as long as the base is bigger and able to go faster.
Right, eventually. We weren't able to see that even at like 10 to the 20th. It still looked like 2 to the k or 2 to the x was a lot larger than e to the x over 5. But eventually, and maybe if you have time at home, you can just keep zooming out. It might not be the capability of Desmos to even go that far.
Is there a way you can find that number otherwise, or is it just by you gotta look at it?
Plug in
Like where it overtakes?
Yeah.
I mean, we could figure out where they're equal to each other. And then when they're equal to each other, we could just test on either side to see which one's larger. Yeah. So I don't know, let's just say that L'Hopital's is inconclusive. So really, we're back here again, trying to answer this question. Let me just kind of put this in, separate it a bit. So we're going to say that's 0 by growth rates. So we've got, this was our capital L. Capital L is 0, and what does that mean? Let's just go back to the limit comparison. Here's capital L is equal to 0, and the chosen series converges. The given series converges. So we've got a limit that's equal to 0, and the chosen series converges, the given series converges. Okay. So we'll say since capital L is equal to 0 and B sub k converges, the given series converges. So it may, if you end up with like choosing the first route where we chose like something comparable to the first series, just a little bit more lengthy to determine the convergence of the chosen series. Here we chose a pretty straightforward geometric series that we could tell whether or not it converged or diverged really easily. But maybe you end up with this limit that's a little bit more difficult until you remember growth rates, which makes it a lot easier. Okay, still same conclusion. Does anyone have any questions on that? So same example. In 5. This time let's choose a series to compare to that's, let's say 1 over 100 to the k. Let me see if I want to. I'm just trying to cover like all 3 of those scenarios mentioned in the limit comparison test. We've seen 2 of them so far when the limit was finite, it was 1. When the limit was 0, and the other one was when the limit is infinite. Yeah, this will suffice. So what do we know about the series 1 over 100 to the k? It converges, it's geometric. Okay, and then when we compute the limit, this time, our A divided by our b, or times 1 over b, what would that limit be? Infinity, right? Because the leading term up top is 100 to the k. The leading term on the bottom is that. So again, by growth rates, larger base grows faster than the e. This is an infinite limit. And so in this instance, what happens? What's our conclusion? If the limit is infinity and b sub k diverges, if the limit is infinity and b sub k diverges, then the given series diverges. But that's not what we're looking at, is it? We've got our limit being infinite, but b sub k converges. So what does that mean? It's inconclusive, right? This doesn't tell us anything.
Picked wrong.
Yeah, you just chose the wrong thing to compare to. So L is infinity, but b sub k does not diverge. The test is inconclusive. So that means either, in this case, either choose a different test, or as we've seen, just choose something different to compare to that actually gives you something meaningful. Does that make sense? You don't have any questions on either of those?
Would you recommend choosing base that's small?
I would recommend, like, for these comparison tests, just to choose something that's really comparable. So, like, I would have just started off with 7 to the k over e to the k over 5 like we did initially. A little more work on the front end, but it's I think it's a little bit more clear once you reach the conclusion.
Only one of these tests has to be like proven, or it to be like abstract.
What do you mean?
Really, you wouldn't have to go through 2 different tests in order to be like this.
Right.
One of them is guaranteed.
One of them does, yeah. So if one of them leads you to a definitive conclusion, converges or diverges, that's all you need. But we've seen instances, the reason we have different tests is because there are situations where certain tests may not even apply, and or that you might end up with an inconclusive result, so then you have to use another test. But as long as you can come up with it converging or diverging by one of these, it's enough. You don't have to use any more than that. Yeah. It's a good question. Any other questions? All right, so what we have so far, we have geometric series test, we have our divergence test, an integral test, our p-series, our direct comparison test, and our limit comparison test. This doesn't even mention anything about telescoping series, so we also have those as well. Again, not to overwhelm you, maybe to strike a little bit of fear that there is a lot that we're talking about, so you should get on this as soon as you can. But, so what do we have? We've essentially have three different tests left to talk about. Fortunately, when we move into the next section, chapter 11, we really only take 2 of these with us. And the geometric and 2 other ones. So we don't take all of these with us. But in chapter 10, we need to know all of these. I think that one's pretty straightforward. It says use the test of your choice. to determine if that series converges or not. So it is a convergent. If you're attempting that one at some later time. But we're gonna end 10.5 with that. Is there any questions on 10.5 before we move on to 10.6? No, all right. So 10.6, I initially thought we were going to do 10.7 first, but 10.6 actually has a theorem that we need to use in 10.7. So we're going to look at 10.6 first. And 10.6 deals with an alternating series. So in 10.6, we come up with an alternating series test. Up to 10.6, we've just dealt with the series that have positive terms. So now we'll look at series that don't have positive terms. And the first series we're going to look at is the alternating harmonic series. When we looked at the harmonic series, just 1 over k, did the harmonic series converge or diverge? Diverge. 1 plus 1/2 plus 1/3 plus 1/4, that series diverges. We showed that using the integral test. But here we're looking at the alternating series, the alternating harmonic rather, 1 minus 1/2 plus 1/3, etc. I'm really going to do a whole lot with this at the moment. The first 4 partial sums, I'll just write out. First partial sum is 1. Second partial sum is 1/2. 1/3 is 5 over 6. And the fourth is 7 over 12. We'll test this in a minute with the actual alternating series test. We're just kind of using some of these, the terms and the sequence of partial sums to come up basically with this figure here. And so here's the first term, a sub 1. Here's the second term, a sub 2, and so forth. There's 3, there's 4. And really, one of the ways, part of the proof for the test itself is based on this idea. If we split up an alternating series, this one in particular, and we look at the even terms versus the odd terms, we see that the sequence of even terms and consequently the sequence of even partial sums is bounded from above. The odd bounded by below. And so we say the even partial sums we'll call S sub 2k are non-decreasing and bounded above, so it converges. Remember we had that bounded monotonic, a bounded monotonic series converges, like inverse tangent, or I think that's the one we used in class. But we've got a bounded sequence that's non-decreasing, it's monotonic, it's bounded, it converges. Same thing for the odd partial sums, bounded, it's monotonic, so it also converges to a different, for the moment we'll just say it converges to M, a different limit, because at this point we don't know, do they actually converge to the same limit? So the odds converge to, so we'll say these up here converge to M, and the evens converge to capital L. And then to show that it actually converges, we have to show that M and L are the same value. And so that's where when we put these together in the following way, the 2kth partial sum is given by this formula. You can verify that if you want to. And so when we look at the limit at infinity, what we get is this limit being L, this S sub 2k minus 1 is M, and on the nth term itself. or the kth term rather, is 0. So what that shows us is that the L and the M are actually the same value. So the alternating harmonic series converges because the even terms and the odd terms both converge to the same value. Whatever L and M are, it's the same thing.
Could they both converge to the distinct different values?
They converge to the same values.
Could
So
they?
could they converge to different values?
Yeah, but like solid values.
No. So like if the evens converge to 5 and the odds converge to 3, we have a divergent series because they're not converging to the same thing. The even and odd terms in this case actually make up that whole series. So yeah, different values it wouldn't converge. So, you know, the alternating harmonic series converges, which, you know, it might strike you as odd, it might strike you as intuitive, but we saw that the harmonic series itself was a divergent series. When we alternate the sign, now we get a convergent series. There's particular terminology surrounding those two outcomes that we'll talk about in 10.6, but that's later. So the alternating series test says we've got this alternating series sum of -1 to the k plus 1 times a sub k converges providing two conditions. One, the terms of the series are non-increasing in magnitude, which means a sub k plus 1 is less than or equal to a sub k. And notice that it says for some k greater than a capital N. So it just says that the series may not start out with the terms that are non-increasing, but eventually that's what has to happen. So maybe after like k equals to 1,000, the terms start to be non-increasing. Okay, so it just at some point they have to do so. And the limit as k approaches infinity of a sub k has to be 0. So someone tell me why that second condition is not the divergence test. It's subtle, but it is not the divergence test. If I write it out, it may be helpful. Divergence test for some series says that we have to compute the limit on the terms of that series, right? So how come this isn't the second condition?
That one could converge to a different term of 0.
Which one? This one? Oh, yeah, so like if this is not 0, then a sub k diverges. But when we see this limit right here, this piece, it certainly looks like this piece right here, doesn't it? But it's not really the same thing. Why is that, Al?
Because of the second clause in the parentheses, k greater than something like that.
Say that again, the second clause where?
In the parentheses for k greater than some index n. In other words, it could increase up to this index n and then start decreasing then.
So yeah, it's a good thought, but no, it's not quite that.
With the other test, if it equals 0, it's inconclusive.
Right, so with the divergence test, if it was 0, it was inconclusive. But with the divergence test, we said if we're given this series right here and the terms approach 0, that wasn't enough to guarantee convergence, right?
Well, this is.
although it says that this is part of it. It says if these terms go to 0, then that's a condition for convergence in an alternating series. Remember here we said let's restrict these series to a series that has positive terms. So if you'll notice, what is this a sub k here in this series? That a sub k isn't the entire series, is it? The a sub k is just the part that doesn't alternate. So when you use the alternating series test and it says, is a sub k plus 1 less than or equal to a sub k, and does that limit on a sub k go to 0, you're totally ignoring the switch part, the part that changes the sign. And all you're testing is the terms of the sequence itself, rather. So that's very, very important. The alternating series test doesn't actually involve us testing the entire series with the switch and everything. This thing right here was the divergence test because we said a sub k itself is that entire series, whatever that series happened to be. And we did see an example earlier in chapter 10 where we did have like an alternating series like this. So we had an alternating series like that, and we said, well, if I apply the divergence test on this entire series, then that's exactly what I have to do. What's the limit as k approaches infinity on the given series? That's the divergence test. So whatever series you're given, whether it alternates or not, the divergence test says you have to compute the limit at infinity on the series that's given as is. But the condition here in the alternating series test says we don't consider the alternating part. We would just consider the k plus 1 over k or whatever it happens to be. So is that clear, like why that's not the divergence test? Because the reason this is not the divergence test in condition 2 is simply because you're not testing that entire series, -1 to the k plus 1 a sub k. That would be the divergence test. Okay, so there's potential for confusion here. A series with positive terms, like we saw when we first introduced the divergence test, the limit at infinity equaling 0 does not imply convergence, but here it's a part of convergence. When the series, when the terms of the series aren't all positive. For an alternating series with non-increasing terms, remember this non-increasing terms is that first condition. Non-increasing terms, the limit on the kth term going to 0 does imply convergence. So are there any questions or comments on that? I do have on the next page 2 examples of when that alternating series test would be inconclusive. By and large for us though, the series that we see, if they are all alternating, it's she sells by the seashore, then it'll apply. Like they're not going to give you like something that's inconclusive. And if it is, we'll see that like just the regular divergence test would tell us that it diverges.
If you get a different limit, it's a number, that means it diverges, right?
If you what? Sorry.
If the limit is not 0,
Right.
it still diverges if the limit is not 0.
If the limit is not 0, right. So here, yeah, it would say that, so like if we have a series with non-increasing terms, condition 1 is met, but condition 2 fails, like say this limit is equal to 2 or 1,000 or whatever, then yeah, it's the test wouldn't tell us anything. We couldn't say that it diverges. I don't know if that's what you were asking, but yeah,
Okay.
in this particular context.
Yeah, so if you have
Yeah.
an alternating, you can't just test the limit on the non, like the A sub k.
Right,
If you test the limit on A sub k and you get a number, that doesn't tell you it diverges.
doesn't tell you.
Okay.
Right. So both of those conditions have to be met in order for this series. That's the assumption, right? It says the alternating series converges if 1 and 2 are true. If 1 and 2 are both not true, then the alternating series test doesn't tell us anything. Here's a sequence of partial sums. We're going to come back to this and look at it as it unfolds in kind of real time when we start talking about the remainder or the error in the alternating series. But for now, let's use the alternating series test to determine if the alternating harmonic series converges. So I'll just abbreviate that alternating series test. What is our A sub k here?
1 over k.
Just 1 over k, right? We ignore the alternating part to determine what A sub k is, specifically for the alternating series test. Okay, then we've got 2 conditions to verify for convergence. One is A sub k plus 1 less than or equal to A sub k. And 2, what's the limit at infinity on that term? All right, so let's write out A sub k plus 1 with this being our A sub k. A sub k plus 1 is 1 over k plus 1. And A sub k, of course, is 1 over k. So pretty straightforward to say that 1 over k plus 1 is less than 1 over k. That condition is met. And what's the limit at infinity?
0.
Right. On A sub k, it's equal to 0. So we've already said that the alternating harmonic converges, but here we're showing it again using the test. So since it's non-increasing and the A sub k approaches 0, that series converges by the alternating series test. Any questions on that? All right, so here's when the alternating series test is inconclusive. 2 examples. The first example, it fails the condition where A sub k plus 1 is less than or equal to A sub k, because we have the oscillations. So like this term is less than this term, but this term isn't less than this term. I don't know where they are, but remember that condition is just saying, is it non-increasing? And we do see these fluctuations or these oscillations do get smaller and smaller. But even out here, depending on how we zoom in, it's still fluctuating like that, even though they're smaller and smaller. They're eventually flat as condition 2 our a sub k is this, this sine k plus 1 over k. So that does equal 0. How do you show that that's equal to 0 when sine of infinity does not exist?
It's bounded.
It's bounded, right? Yeah, so we use the squeeze theorem, right? Squeeze theorem to show that. But both conditions are not met, therefore the alternating series test is merely inconclusive. We wouldn't say that, well, both conditions aren't met, therefore it does not converge. That's not your conclusion. Your conclusion is just that it's inconclusive. Okay. Second example, it is non-increasing. Condition 1 is met, but it fails in the sense that the limit of 1 over k plus 1, this is our a sub k. That limit is equal to 1, not 0. So, like, you know, we would say that based on these two conditions, the alternating series test is inconclusive. However, I maybe should have left some more space. However, if we look at the divergence test, where we look at the limit at infinity on the entire series with the alternation part and everything, it's going to be 1 or negative 1, which is clearly either way not 0. So by the divergence test, it diverges. So even though the alternating series test is inconclusive, then we have other tests we could use. And we'll, in fact, we'll see when we get to 10.7, those two tests that we carry on into chapter 11 are presented with absolute values in place. So even an alternating series could be put into a test that we see in the next section. And the reason we care about that is because, you know, like, just right quick before we take a break, the idea is that we're going to look at like a conversion series. Let's say this one, 7k plus 100 over e to the k over 5 minus 70. What we're going to do with that is then we're going to put a variable x in here and say, well, depending on this variable x, does this actually equal to some function? If so, what function does it converge to? We got to know like what this converges to. Since x varies, it can be positive or negative. We want to look at tests that involve absolute values, so we can say for sure. It doesn't really matter where x is. I mean, it does matter where x is, but when we start looking at variables intact with a series, it becomes all that more important. So anyways, is everyone clear here? This is the divergence test. Second condition here is just the second condition for the alternating series test. You can see the difference between the two. Are there any questions on what we've done so far? All right, let's take a break. We're going to skip example 2. It's a little, if p is larger than 1, it's pretty straightforward, but the other conditions on p, not so much. So we're going to skip that one. And so you use the alternating series test to determine if the given series converges or diverges. So why don't y'all give that a shot? be able to determine that statement for sure. So how else could we do that? Because if we're just comparing these two, if we're saying this versus this, which one, which way does it go? So like that or like that? How else could we know that? Like something definitive we could use. So remember, it came up in the integral test. Yeah. So just a word of mention here. When we say that the terms are non-increasing in magnitude, as we see with this example, that might be a little bit more difficult to establish. We'll look at a graph too to show that it's really not a trivial thing. Just to say, well, since this is ln of k plus 1 over k plus 1 over a larger number, that this quotient is smaller. I mean, that I don't think that's clear in this case because they're so close to one another. But just like in the integral test where we said that those terms have to be decreasing, when we say that these terms are non-increasing, well, non-increasing is pretty much decreasing, right? Non-increasing means that it's either decreasing or constant. So to test if something is decreasing, just like with the integral test, sometimes you might have to look at the first derivative and test that way just to make sure. So here, I'll show you the graph of both of those. The continuous aspect anyways. Here's ln k plus 1 over k plus 1 in green, and in purple, the series that we're given. So, we're way out here, and this is like, we were originally at a 1-to-1 scale, but even when we look at a different scale, it's not clear which one's smaller, which one's larger, right? So you have to get really, really close because they are really, really close in value. Let's see, what is that difference? It's about 0.1 difference. So I don't know it personally. If you just say, yeah, that first condition is met with this particular a sub k, it's really not a convincing argument. So in a case with the last example, clearly 1 over k plus 1 is less than 1 over k. I don't think there's any debate about that. But this is a little bit more tricky to justify or to just eyeball. So with that in mind, then probably should use the first derivative on that. Just put a question mark above those because that's what we're trying to answer. I think everyone should have gotten this one all right. So just using growth rates there, you can use L'Hopital's if you want, but that limit is 0. Okay. So run through this first derivative. No, not quite. So our first derivative. Then we figure out where does the first derivative equal 0. Remember, the interval in question is from 1 to infinity. So when is our first derivative 0? When does the ln of x equal 1? When x is e.
Or whatever.
So that's when your first derivative is 0. I mean, we can test what happens before just to see. So the first derivative, I don't know, let's say let's test 1 over e. Wait, is 1 over e? 1 over e is 0.6. So that's not, I don't know. Okay, we'll just punch it in our calculator. So let's test 2 and, I don't know, e squared. So when 2 is plugged into the first derivative, what do we get? .08 positive. So from the term 1 and the term 2, what does that mean about our series, a sub k rather? The first derivative's positives means that the function is increasing. So the first two terms of that series increase, but how about when we plug in e squared, some value after e? It's 1 minus 2 over a positive number, so you get a negative number. And that was the only critical value we came up with, so that means after a value of e, the first derivative is negative, or after a value of e, the original series is decreasing. So we'll say that after, you know, and we're translating this in terms of k, but after k equals to e, and we don't use irrational values anyways, but after k equals e, ln k over k is decreasing. That is, a sub k plus 1 is less than a sub k. So we do have a non-increasing series rather after e. The limit is 0. So both of these conditions are met. Since both conditions are met, the alternating series test says that that series converges. Yeah, because the series is increasing.
So why doesn't that like cancel it out? Because like the whole spectrum of the graph is considered in, right?
What do you mean, like what cancels out?
So like if you're going from like starting at 1 and like from there until e it's increasing,
Yeah.
doesn't that make the like argument false?
No, because it says, go back to the test. It says that the terms are non-increasing in magnitude. In other words, that's true for some k greater, for a k greater than some n. So what it says, the way we interpret that is that it eventually has to start,
Decreasing.
to be an, yeah, right.
So yeah.
So what?
Is the end behavior?
Yeah, it's kind of like the tail. And it doesn't say, it just says for some index capital N. That could be, as we saw at the third term, it starts to decrease. It could be at the millionth term, it starts to decrease. But yeah, eventually it has to.
It kind of goes along with what you were saying on page 3, where it's kind of like bouncing. It continues to bounce throughout. There's not a time that it ever hits decreasing.
Right, yeah, so this thing here was an example of something that wasn't eventually decreasing. Even though those oscillations get smaller, it's still one term is, this term here is larger than this term here.
Yeah, but this one
Yeah.
does eventually decrease. It's just after E.
Exactly,
Okay.
yeah, right. Yeah, so does that make sense? Anybody have any other questions or need clarity on that? Okay, so this eventually does decrease, and then the series converges. By the alternating series test. All right. So we saw this with the harmonic series, but it was sort of verbose, so I just took this out of your textbook. There's two different ways to classify a series. So in this final segment, introduced, this is actually needed in chapter 11. So this is chapter 11, not chapter 9. We need a notation. Sum A sub k denotes any series, positive terms, alternating series, or whatever. But that's the notation for any series. And so they say that we're looking again at the alternating harmonic series, which converged, but the harmonic series was divergent. In contrast, another example, we have an alternating P series where P is larger than 1, converge, and the P series itself, 1 over k squared, converges. So you have these two instances where a particular series with the addition of an alternating part may converge, where the original series without an alternating part diverges. Or in the case of the 1 over k squared series, adding an alternating into the series didn't affect its convergence. So you got two different outcomes there. Either putting an alternating in a series affects the convergence, or it doesn't affect the convergence. And so both of those situations we're classifying. I don't know if it's actually classified here or not. Yeah. So these examples illustrate removing alternating series, or alternating signs rather, may or may not affect convergence. And so what we get is this definition, this classification of two different types of convergence, an absolute convergence or a conditional convergence. In the case of an absolute convergence, we're then going to look at an absolute value of the series. So particularly if we apply that to an alternating series, when we take the absolute value, it doesn't alternate anymore. So if the absolute value of a series converges, then the series without an absolute value also converges. And so what we're saying that it converges absolutely. And what we'll see is the theorem that's presented in 10.6 that we need to carry over to 10.7, that we need to carry over to chapter 11, is the fact that if a series converges absolutely, then it converges. If the absolute value of the series diverges, so think of this one here as the harmonic series. We take the absolute value of the alternating harmonic series, we get the harmonic series. So if that thing diverges, but this thing maybe with the alternating part, like the alternating harmonic, converges, while the other one diverges, then we say it's conditionally convergent. The condition there in that instance is, the condition for convergence rather in that particular instance is that we have to put that alternation in there for that convergence to happen. Does that make sense? Does anyone have any questions or comments about that? The weird thing with, we don't deal with like sums and stuff, but the weird thing about conditionally convergent series is that you can get them to sum to any value you want. So it's really bizarre.
Wasn't that just because you're choosing which terms you want to add in a conditional sense?
Yeah, right. Like if I group these first 3 and then these next 5 and then the next 12, you're gonna get a different sum. Yeah, it's really weird. There's if anyone's ever heard of the band Tool, they have a song called Cesaro Summability. Is anybody into that band at all? So like there's a Cesaro Summability, which is one of the things that mathematicians did do to look at like conditionally convergent series, where you try to make sense of something that could really be anything, but then you try to hone it into like, can I make sense of something that doesn't really make sense, is kind of the idea. But we don't deal with that. It's just a really weird thing to note. So then they're going into a little bit more detail here with the series that they started with. Granted, we didn't look at the 1 over k squared and the alternating 1 over k squared, but both of those converged. The harmonic diverged, but the alternating harmonic converged. So the situation we have here is absolute convergence. If the sum of the series converges and the absolute value of that also converges, then you have absolute convergence. Really, in practice, absolute convergence, we just look at that. We just look at the absolute value. Conditional convergence, if the series a sub k diverges. Again, think about that as the harmonic series, but the
Is it the other way?
the absolute value, yeah, sorry, the absolute value is the harmonic series, because that's going to eliminate the alternating part. The harmonic series here would diverge while the alternating harmonic series converges. That's when we have conditional convergence. All right, so to put that in practice, determine whether the given series converges absolutely or conditionally. So to determine that, you've got to test 2 series. You've got to test the series as it is, and the other one you have to test the absolute value of the series. So the series in 1, the sum of a sub k is just the series as it's given to us. So in order to test this, sum from k equals 1 to infinity, negative 1 to the k plus 1 over k to the 3/2. That is an alternating series, so we have to use the alternating series test. So here, condition 1 is a sub k plus 1 less than or equal to a sub k. What is a sub k for this alternating series?
1 over k to the 3/2.
Yeah, 1 over k to the 3/2. So we're trying to answer the question then, is 1 over the quantity k plus 1 to the 3/2, and what is that in relation to 1 over k to the 3/2? Is it less than or greater than? It's less than. Do you all agree with that? Okay. So hopefully that's pretty straightforward. You know, you might want to think about it as what is k plus 1 to the 3/2 in relation to k to the 3/2? Or start off with k plus 1 and k. Clearly k plus 1 is larger than k. If I raise that to the 3/2, they're still larger. Then I take the reciprocal, I flip the inequality. So I don't know, there's a few ways to think about that. But yes, this condition is met. I'll just say since. And 2, it's the limit as k approaches infinity on a sub k equals 0. A sub k is 1 over k to the 3/2. Yes. Clearly equal to 0. So what we have is the series itself converges. We have to then look at the absolute value of that series to determine if it's absolutely convergent or conditionally convergent. Yeah, good enough. So in this case, we're actually looking at the sum from k equals 1 to infinity, the absolute value of that entire series. So when we take the absolute value of an alternating series, it just doesn't alternate anymore. And what do we know about the series 1 over k to the 3/2? Yeah, it converges. How do we know?
Prior part. We just did that.
Well, we tested the alternating series, right? Just because the alternating series converged doesn't mean the series itself it converged. Like if this series were the alternating harmonic, we would say the alternating harmonic converges, but this here would output the harmonic series and it diverges. So the question is how do we know if 1 over k to the 3/2 converges or not?
Just a p-series, the spirit of it.
It's a p-series, right? Converges, p-series, where the power is larger than 1. So the absolute value of the series converges, the series itself converges. What would we say about this series? Yeah, it converges absolutely. Since, we'll just say here, since this and this converge. Any questions on that?
So, just based off that first test though, we know that it's gonna converge
This test here?
on the left side, yep. Just
No,
because of that, no, we don't.
you don't know.
Okay.
So the alternating could converge. Like, if this were this sum, again, if this were the alternating harmonic, that alternating harmonic series would converge, but the absolute value would be just the harmonic series, which would diverge. Does that make sense?
Yeah.
Yeah, just because the given series converges doesn't mean that the absolute value of the series will converge.
So what's the difference between when we were testing that first one before, and like, just by doing those two conditions, we knew that it was gonna converge?
Yes.
What's the difference between them?
Right, so this is, like, if we just looked at this one on the left, if we just were given that series and it says, determine if that given series converges or diverges, that's it.
Then we're good to use-
Then we're good to go with this one on the left,
Okay.
right? But if it says, does it converge conditionally or absolutely, then we have to look at the series itself and the absolute value of the series.
So once that absolute value comes up, then it kind of like cancels out the A to C on the first half.
Right, right. Yeah, so yeah, that's an important thing, that when we say that if this series converges, or let me see, how do I want to word that? So if we know that this series converges, it does not imply that the absolute value also converges. However, if we look at the converse of that, if we know that the absolute value converges, then we know the series converges. So this converging does imply that this series converges. Yeah.
So if we're doing this test, why don't we just do the absolute value one first? And then if that converges, then we just know that one converges.
Yeah.
That like saves
Yeah.
half of the work.
Yeah, you can. But technically that theorem hasn't come up
Oh,
yet.
I'm just-
If we're like progressing through this material linearly, then yeah. In practice, you can just look at the absolute value, because absolute convergence, in other words, we'll see the theorem, absolute convergence implies convergence. So yeah, we could say, once we know that, which in theory we don't know that yet, we could just start with this one. And if this converges in absolute value, it means the series converges absolutely. Yeah. Valid point. I mean, very astute observation. But yeah, once we see the theorem, we're good to go.
Okay, cool.
Yeah.
So like on the exam and things like that, we're gonna have some beginning up in, right? So we can just skip that. next
Yeah, yeah. Yeah, I think it's important to know like the ins and outs.
Before you give us the cheat codes.
Yeah, right. Right, yeah. You remember the Power Glove?
Yeah.
Anyways, I'll try this one. Alternating ln over lnk, does it converge absolutely or conditionally? And there's the theorem. And I think this is a good example to show, why if we just started off with doing the absolute value, how that could maybe lead us to a false conclusion. Halloween prison. You know who you are. Somebody wrote that.
I thought you wrote that.
No. But yeah, yet another Halloween I miss out on family stuff.
Just cancel class again.
Hmm?
Good cancel class again.
Yeah, right. I mean, I could have.
I don't think he canceled it before. He made him cancel it.
Oh, don't think my bosses and the higher ups would appreciate it.
Don't you get so many sick days?
Huh?
Don't you get so many sick days a semester?
Yeah, I do, but no one ever can sub my classes, so.
So you could reference us. You could reference us to a past lecture.
Yeah, I could. Always scheming.
How much proof do you want for the conditions?
As much as you can. Justify as thoroughly as you can. I mean, I think if it's obvious, like 1 over k plus 1, 1 over k, you know, that kind of situation's pretty obvious.
So like, that'd be pretty obvious to me.
Yeah, I think so. I really need a little more there.
I guess it's actually that and have proof. That's what I was looking at. I think if you use the comparison test and you do like the same as you did over here with that LNK plus 1, since that's less than the LNK, then
I don't know why.
it should mean that it's also convergent.
If less than something, which is less.
Yeah, if A, K is, no, is that supposed to be times?
I know it seems like we're just testing one over LNK here, but this is kind of so like this is test, this is obviously we just don't test that portion of it. This is the algorithm. The series goes from LNK. Because if we did this here, we got that bonus. Test, and I would say that it's.
That's no. No. I don't think it matters.
So these
I don't think
two
it
conditions that you tested here are only the whole. If that wasn't actually included, we would That's a totally different series, just like the one we did. The whole
So that is the breakaway. And then how many years would you do transfer?
So what did you say about this? This is the alternate series convergence, right? So what about this one? Is it convergent? Okay. The thing is that yeah, but the divergence test isn't sufficient. It needs a But your terms are getting smaller, it doesn't need the divergence. So, it's not. So it's just for Yeah, exactly. Okay, yeah, so you can show that this is convergent. P series you're comparing to. And what is that? Yeah, exactly. So you've got a convergent series. It's infinity.
I think so. Using that comparison test,
Yeah, right.
setting that to ln k plus 1, since that's less than the given,
Yeah.
that diverges, that would diverge.
So you're comparing, if you're comparing this one to this one? Yeah, so like the chosen series that you're gonna compare to, you have to know if that converges or diverges. And so answering the question, does the chosen series converge or diverge, is virtually equivalent to asking if the given series converges or diverges.
Okay.
So you want to pick a different series. So when we look at this series in particular, when we do this, all that is on this series is the divergence test. Right? So it's like inclusive. Testing this series or comparing this series to that one is they're virtually the same thing. Right? So if I pick this series and I say I have to know something about it, knowing something about the convergence or divergence of this is going to answer this question. So that's really not doing us any favors to take that. So we'll find that chosen series. So again, for the series itself, we're just going to use we have to use the alternating series test. We have to use the alternating series test. This one. So, this. For the alternating series test, we're just looking at our a sub k being 1 over ln k. So it's 1 over the natural log of k plus 1 in relation to 1 over the natural log of k. Well, the natural log of k plus 1 is larger than the natural log of k. So we'll say that since and really that's enough justification for that. If you want to do the derivative and stuff, that's perfectly fine too. There's nothing wrong with that. And the limit on that term one over something arbitrarily large gets arbitrarily small. So both of those conditions are met, which tells us that the original given series, the alternating series itself, is convergent. So we'll just write it there. And so you want to be careful when you go to test the absolute value of the series, because the absolute value of the series does actually give us, and it will always give us something similar to what we've tested in the alternating series part. But we can't just go off of these two conditions in the alternating series test to infer anything about 1 over k by itself. Because 1 over ln of k by itself is a completely different series than what we've tested here. Because these two conditions in the alternating series test, again, they only account for this portion of the series that was given to us. So, you look at this 1 over ln k, and if you're saying that it converges based on what you've done over here, it's not correct, because they're two totally different series. One's alternating, one's not. It's not geometric, it's not telescoping, it's not a p-series. To integrate 1 over ln of x might cause a little bit of problems. We could try by parts. So then after we've exhausted those options, the next test we ran into were the comparison tests. So if we say, all right, well, I'm going to use a comparison test, and so some folks were choosing the B to be 1 over ln of k plus 1, which doesn't, choosing something like that doesn't help, because if we know what 1 over ln of k plus 1 does, we know what 1 over ln of k does. So answering the question, does the 1 over ln k converge, and picking a series like this that's super similar to it isn't doing any favors. So you want to pick something that you know converges or diverges pretty easily. So the series that I saw that someone was close with was comparing it to 1 over k squared. So if we compare 1 over ln k to 1 over k squared, we know that this series converges. Convergent p-series. However, when we compute the limit, k goes to infinity of the given series divided by the chosen series. Notice that limit then gives us, by growth rates, that limit gives us infinity. If the limit in the limit comparison test is infinity, the chosen series has to diverge before you say that the series given diverges. But that's not the case. The limit is infinite. The series we chose converged. So if we're going that route, there's nothing wrong with our computations. Our conclusion is inconclusive, though. So we might say, all right, well, that limit was infinite. It didn't yield any fruits. Let me try comparing to 1 over k. We know 1 over k is a divergent series. It's the harmonic series. Is the limit still infinity? Yeah, the limit is still infinity. So we've got an infinite limit, and we're comparing that with a divergent series. So then we can conclude by the limit comparison test that 1 over ln k diverges as well. So since the limit is infinite and the chosen series diverges, the series 1 over ln k diverges as well. This is why I think it's important to know the tests and as opposed to looking for shortcuts, because a lot of things with these series aren't intuitive. There are some things that are intuitive, but I think by and large it's not really intuitive. So that's why we have all these tests to tell us definitively whether or not something converges or diverges. Anyone have any questions on what we've done? Yeah.
So is that the 1 over ln to kx, whatever, is that divergent just because it doesn't reach 0 fast enough?
Right. It actually grows slower, it grows more slowly than the harmonic series, or decreases rather more slowly. Because ln of k by itself grows so slowly compared to like k itself, just like that linear function versus the logarithm. So we've got the series converging, but the absolute value diverging. So if we started with the absolute value instead of diverged, notice there's nothing we can conclude. Just because the absolute value of a series diverges doesn't mean its non-absolute value counterpart diverges. 'Cause we see that here. One converges, one diverges. So we would actually say that the series that was given is conditionally convergent. Given series, therefore, given series is conditionally convergent. Okay.
Say like why which test, or can you just leave it as that?
Just, yeah, we've actually just have, it's conditionally convergent because this series converged, but the absolute diverged. Yeah, it's all right. All right, we'll pick up here on Tuesday.
But